Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is from Exludus. We have Dale Geldart, who is the CEO of the company. So, Dale, welcome to the show.
Thanks, Rich. Nice to be on the show.
Well, I really appreciate you coming on. We're coming up here to the next holidays, so
Great. Well, thank you very much for the introduction. And what I'm going to talk about today is technology we've developed that is aimed at helping people make better use of the growing numbers of cores that we're seeing in servers across the HPC community. And we've developed a series of tools that we label multi-core resource management tools that help people better utilize the cores within the system and tap into that aggregate processing capacity. So on slide 2, just a real brief overview of the portfolio of products that we offer. Essentially, under this umbrella of intelligent multi-core resource management, we have 3 discrete components. One which adds an intelligent kernel-resident workload management function to the Linux system. And the second product is an ability to layer dynamic containers on top of that functionality. And the third piece is, as we learn about how jobs consume resources at the job, process, and even down to the individual thread level, we capture this fine-grained information and we make it available to users to learn more about the jobs that they're running, which may help them better fit this work into their environment and really provide a wealth of information through this database that we maintain of this resource consumption information. So what does this all mean? If we look at the next slide, there's some highlights of what the functionality delivers. And the main point that I would emphasize is that our MCOpt suite allows people to safely maximize system utilization. So really our goal is to allow people to use as much of that compute capacity as possible without getting into serious resource contentions inside the system that may degrade performance, may actually even negatively impact application or even system stability. So there's a number of features and functions that we add to the system through our product suite. And without belaboring this list, the main goal is to allow you to get more work processed in less time by safely using more of the system processing capacity. So in terms of implementation, on this slide, we basically have highlighted how we fit between the applications and the operating system. The key point here is that installing the MCOpt functionality is very simple and low risk. We install as a loadable module, really sitting between the applications and the operating system, and you do not have to make any changes to either of those points. So no changes to the applications, no changes to the operating system. We're basically adding this new intelligence into the kernel. So you continue to use your existing workload manager at the cluster or cloud level, whether that's LSF or Grid Engine or the various tools that people use to distribute work across the cluster environment. And then we're running inside each individual system, trying to ensure that we get the most out of all of those processing resources inside each individual machine. The really nice thing about the approach that we've taken is that there's very little administrative learning curve. You can install the MCOpt functionality and be up and running in literally a matter of hours without having to make any serious changes to the environment or without having to go through a lot of training or education on how to make use of our functionality. Just briefly on slide 5, you can really equate what we're doing inside the kernel a bit to traffic management that you might see driving through a city. These are actually pictures from Manhattan. But if we look at large-scale traffic management problems, cities take advantage of fairly simplistic traffic light synchronization to try to move traffic through the city in an orderly fashion. What our MCOpt functionality does is applies similar queuing theory concepts into the kernel, But we've developed a series of algorithms that try to best fit the work that comes into the machine to those resources, avoiding the gridlock or contention to resources. So a good example of that gridlock might be an example of getting into a memory oversubscription problem where you can see the CPU utilization fall to close to zero from an application processing standpoint, and therefore work really grinds to a halt. We're doing a much more sophisticated job than simple traffic light timing. We're continuously monitoring the activity that's taking place in the system, and then we're dynamically changing traffic patterns, changing resource accesses based on what we see as then current conditions. So I mentioned one of the problems that we look at is how do we use memory more effectively. So on slide 6, we've got a simplistic example here of a plot of an application. This was actually taken from a chip design application where the blue, green, and yellow are each individual job's memory usage over the execution time of the job. These actually happen to be very long-running jobs, but they build up to a peak memory usage of about 48 gigs and then level off to some much lower memory usage. So if I'm running these jobs inside a 64 gig server, I actually, at steady state, could easily and comfortably fit 3 of these jobs into a system. But most people will avoid doing this because they can't control when these jobs each reach their maximum memory usage. And if I get into a bad memory contention problem, I'll essentially oversubscribe memory, and I'll get into a very serious performance degradation problem. May even get to a point where I need to reboot the system. So if we look at what the MCOpt functionality is doing online on page 7, effectively we're continuously analyzing each job's need for memory, and we're making scheduling decisions based on each job's actual then current need. So what we can do is, even if these jobs are all started at the exact same instant in time, which under Linux would quickly cause a memory oversubscription problem, we can effectively stagger these jobs' access to memory, ultimately allowing 3 of those jobs to run where under Linux you may only safely run 1. So effectively you can get much more job throughput through that single server resource. On the next slide, we can see the net effect of this MCOpt functionality. Each color in these boxes here represent a different job that's running in the system at some instant in time. Actually, here we were running 11 discrete jobs, and each one had varying needs for memory and CPU resources. So under a typical Linux deployment, we can see that these jobs ran in about 39 time units. But because MCOpt is able to much more effectively, safely pack work closer together and take advantage of any currently available resource, we end up being able to squeeze more work into the system and end up getting more work completed in less time. So here we've actually reduced the total runtime by about 50%. And on average, we see in most of the environments that we work with, people will realize gains ranging anywhere from 20 to as high as 50% based on the characteristics of their particular workload. We also add some interesting new features and functions into the system that allow people to fine-tune or tailor their workload to the system. So on slide 9 here, we'll talk briefly about an ability to prioritize work in a unique fashion. So here I have running in a system a number of jobs, 4 jobs, each one that have been assigned some unique priority level. And the lower priority number here is a lower value job, so higher number, higher value job. So I have a priority 1, which is a very low priority job. This may be a background job that you only want to consume resources when nothing else is running, as an example. And the thing that's kind of interesting here is in regard to workload management queue priorities, you may spend a fair bit of time building up a number of queues under LSF or Grid Engine that try to distinguish between high and low value work. But as those jobs get dispatched to an individual system, and obviously as we have more cores in the server, we're going to have a wider range of jobs concurrently hitting the system. What we see is that at the kernel level, those workload manager priorities are essentially lost. So now I can have spent a fair bit of time dispatching jobs across a cluster based on some prioritization, but I lose that prioritization once those jobs hit an individual system, and I can have very low value work competing for resources with very high value work. So with our MCOpt functionality, we allow you to carry that priority into the kernel. So now on the next slide, we see that I have a higher priority job, a P10, that I'm going to dispatch to the system. And effectively what it's going to do is push out the lowest priority job, in this instance the P1. And the P1 job on slide 11 will be pushed into a suspend queue. It won't be killed. It will be temporarily suspended and held until resources become available again for it to continue. But the key point here is that I've now allowed this higher priority job to come into the system, preempt a low value job, and get to work sooner than it would otherwise be available to it. And in total, I'm again putting more resources to effective use. On slide 12, we talk about a job exclusivity feature that we add to the system. And this could be really valuable when you're running multi-threaded jobs or parallel jobs where you may define that a job needs to, say, as an example, need 8 slots to process. And so that job will sit in the workload management queue waiting for a system to have enough slots available to it before that job will be dispatched. And we hear from people quite regularly that these parallel jobs or multi-threaded jobs may actually sit in the workload management queue for some extended time periods, waiting for enough work to drain out of this system so that enough slots are free for this job to be dispatched. By flagging through MCOpt a job as exclusive, what you're able to do is, as soon as one slot in a system becomes available, I can dispatch that job, and then going on to slide 13, I can push this exclusive job out into that slot, and it effectively can take over the entire machine. So any jobs that are running will be pushed, as indicated on slide 14, will be pushed into our suspended queue, and that work will sit there suspended until the exclusive job completes its execution. So this can be really valuable if I have a high priority job that I need to get out now. And I don't want that job to sit in a workload management queue for an extended period of time. I want it to be able to immediately grab all the system resources that it needs to execute and get that work completed. And then once that job's left the system, the temporarily suspended jobs will be allowed to continue at the point where they had been suspended. So again, not only putting the system resources to maximum use, but being able to tailor which jobs get access to those resources by flagging jobs as having varying levels of priority, which is carried into the kernel, even to the extent where I can declare jobs as having exclusive access to some level of system resource. On slide 15, we talk about another component that we layer onto MCOpt, which is a dynamic container functionality. This is actually new functionality that we've just released, and it allows you to create policy-based system shares for both cores and memory. Effectively, all cores and memory in the system become a central resource pool, and I can set my system shares in a way to support service level agreements or SLAs that I have with my user community. And by default, we're going to assume that all of the resources are just in a default container. And in effect, MCOpt running on its own, without this dynamic container piece enabled, runs in this default 100% share mode. But then I can allocate to various projects here. I've defined project A is going to have 10% share, project B 25%. I can dynamically change these as needed. I can do this in conjunction with a workload manager, or I can actually do it from an administrative command line. And I can now in this bottom piece have 3 projects identified where A, B, and C have 10, 25, and 50% share accordingly. So this is a very dynamic capability that is based on actual defined needs or defined service level agreements that you have with the user community. The important point is that users will get the level of resources that they've been committed to. So on the next slide, 16, I'll give a concrete example of this functionality in action. So very simple example, and obviously as, again, core counts continue to increase, the numbers of concurrently running jobs and the need to better fit these jobs into available resources is going to become more and more important, and the ability to meet service level agreements is going to become more and more challenging. So here I have just a simple example, 4 jobs running on a 4-core system that has 16 gigs of memory, with the expectation that each job is going to consume 25% of memory. I can see under Linux that 3 of the jobs, which are running at 3.8 gigs each, they actually are below their supposed allocation. And then I have one job, job 4, that actually is exceeding its expected memory use. So in this case, instead of using 3.8 gigs, this one ill-behaved job, if you will consume 8 gigs. Now, you can see the yellow boxes represent how much swap that each job is using, and RSS is physical memory that each job is using. But you can see that even though jobs 1, 2, and 3 are below the threshold that's been established or expected for them, they actually are all penalized by swap activity because this large job 4 has effectively pushed some of their memory pages out, and now instead of running entirely in physical memory as expected, they're having to talk to the swap device. And in general, you're going to see a 30 to 50% performance degradation when you have to start talking to the swap device. The other thing that's important here is that I can rerun this example multiple times, and I will get a different result every time. And by that I mean, in some cases, job 1 will be more penalized than job 2. In the example shown here, job 2 was actually penalized less than job 1 or job 3. So it's a bit random, dependent upon how Linux selects pages to be swapped out. Now, if I turn on the MCOpt container functionality and I designate that each of these jobs are going to have 25% of the system resource, we can control that job 1, 2, and 3 will always run out of physical memory. They will not be forced or penalized by talking to a swap device. So they will consistently rerun after rerun after rerun, get repeatable, predictable performance. The one large job, the ill-behaved job, will be forced to take his excess from the swap device. It is worth noting that even in this case, though, that large job does better from a runtime standpoint than under Linux. And the reason for that is there's actually less contention for the swap device. So even though it's being forced to take all of its excess from the swap device, the reduced contention to that device actually gives it a slightly better result than it would see under Linux as well. Key point here is I can meet my service level agreements, and I can do it in a predictable, reliable manner. On slide 17, just briefly talking about our job profiling functionality. As each job runs, we learn very fine-grained information at a job process and thread level about the actual memory usage of a job and all of its related statistics, I/O statistics, what files it touches, etc. And we push this out into a central database which can be queried by users to learn more about the jobs that they're running. On page 18, there's an example of a thread level report that is showing various statistics at the thread level for these various jobs that we're running. You can also, as depicted on slide 19, you can run visualization tools. These are web-based graphical tools that allow you to plot out interesting data like the actual memory plot of a job over the life of that job. And you can easily drill down into an individual job to learn more about it down to a very fine-grained level. And lastly, before I wrap up this presentation, just a couple of brief examples about real-world performance impacts of turning on MCOpt functionality in a couple of environments. This graph on slide 20 is actually captured, or was actually captured, at a large DOE lab in the U.S. And it's interesting to note that the throughput increase gain is not a steady bar. So the red box is the Linux result, and the green bar on top of that represents the throughput gain through the MCOpt functionality. And this is on a system-by-system basis. And the reason for the different levels of gains is we are actually analyzing in real time what are the actual conditions in each system at each instance in time. So as the mix of jobs change on a particular machine, the throughput benefit of MCOpt will fluctuate. But here we can see that in this environment, the lowest performance gain was about 8% on an individual system, and the highest gain was about 55%. And if you blend it out, it runs somewhere between 25 and 30%, but a very significant performance gain or throughput gain on a range of scientific applications that were being run in this lab. On slide 21, this is an example of an EDA environment, chip design, where I'm running the same workload under Linux and under MCOpt, and we can see that there is about a 30% gain or a 30% reduction in runtime to get the work through the system. And it's worth noting that this was captured without making any changes at all to in-place resource management hints that were being applied at the workload management level. So this actually held back our gains to some extent. By opening up the pipes a little bit more, we probably would expect to see some additional throughput gains there. But 30% is actually a pretty good result for doing a simple MCOpt installation, turning on our functionality, and letting us add this multi-core resource intelligence to the kernel. And that's the conclusion of my presentation. On the last page here, I'll just put up some information about how to contact us if there's any questions or desire for additional information. But you can certainly always feel free to ping us at info@exludus.com, and we'd be happy to answer any specific questions that people might have or thoughts that may have been triggered as a result of this presentation. Thank you very much, Rich.
Well, thank you, Dale. A couple questions. I just wanted to clarify. Does the MCOpt require you to do anything to the application itself?
No, it's entirely transparent to the application, which is one of the real benefits of the technology. You do not have to do any application rewrites to take advantage of the functionality.
Well, good. So I guess my big question is, why isn't the operating system doing this? Is it just optimized for other things?
Well, the operating system has evolved as a fair share scheduling resource, and there's a really interesting component to what we're doing in that we're really kind of bridging the gap between user space and kernel space. So it's really a combined functionality of profiling these jobs as they run and doing that profiling in real time as jobs make each incremental resource request and comparing that against all of the other aggregate requests inside the system. So it's really this profiling plus resource scheduling optimization that we're adding to the system, which is really outside the domain of the operating system itself, which has really been focused on how do I provide fair share access to resources for whatever jobs come into the system at some instance in time. And clearly there are some tools that you can use to try to alter the OS behavior in some fashion. From a priority standpoint, you can use flags like nice to try to change the percentage of CPU that might be allocated to a task. But it's important to note that the nice command doesn't have any impact on memory usage or prioritized access to memory pages. And there are certainly new functionality coming online like cgroup functionality, which is a very static way to try to segment a system. So it's similar to what we've done with our dynamic container functionality, but the key difference being that our containers are very dynamic based on policies that can literally be changed on a job by job by job basis. C groups tend to be much more static definitions, and you can end up with resources that are trapped within a C group, even though jobs running in another C group could benefit from those resources, but they don't have any way to cross those boundaries. Our dynamic container functionality allows you to in essence, cross those boundaries and take advantage of temporarily available resource. So the main distinction is the application profiling in conjunction with the resource allocation, and that's the big value that we add above and beyond what the operating system does.
Sure. So Dale, we definitely are going to see more and more cores on a system. Would your software potentially work on something like the mic architecture?
Oh, absolutely, and we're also looking at how we add our functionality into a number of different devices, like smartphones and tablets, as an example, running the Android operating system. We've actually gone a fair bit down that porting path already, and the technology that we've developed is very extensible both to new processors like the Intel mic architectures, and also looking at things like ARM solutions running on Android on things like smartphones, because you have the same problem. If you have a phone call coming in on your Android smartphone, you need to be able to answer that call, and that actually is a bit challenging for people today.
Yeah. So kind of a wrap-up question here, Dale. As far as getting the word out about what you guys do, what's the toughest nut that you have to crack?
Well, with any new technology, there's always a ramp-up time to get the word out, and we're in the process of that now. I think we're getting some good visibility from the analyst community. As an example, the 451 group just recently did a nice report on our technology, and we're looking at how we leverage the analyst community and how we can get our technology more widely known out in the marketplace. But that's not a unique challenge to Exludus or to any startup. So we're really now in the process of actually building up a sales and marketing team, and really starting to look to put more money into sales and marketing activities.
Oh, terrific. Well, Dale, thank you for coming on the show today.
Well, thanks a lot, Rich. Really appreciate it. Wish you a great 2012 along with everyone else that's listening. Hope everyone has a great and prosperous coming year.
All right. Well, thanks for that. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.